Someone who wants to follow this online now can do. Welcome back. 2, 3, 4 hours, okay. How was the spring break? Enough relaxation? Okay, good. This time of the year is usually a little too busy for anyone, I think. So good luck to you in your projects, and keep us posted. Most of the proposals are great. The ones I looked, all of them are great. So thanks for all the hard work you put on those. Today I'm going to be talking searching and sorting. How many of you know what these mean? Anyone that doesn't? So I didn't want to put some basic slides. Searching is you have an element, you're trying to find it, but the ones we're actually in a list of entries, but we're actually going to do some special version of it. We'll assume that the input is sorted, and you're trying to find some statistics, like order statistics is the name. Just didn't want to call it order statistics because it kind of is a little confusing title. Let's say you want to find the median element. You want to find the 10th highest element. That kind of questions is the order statistics. So you're trying to search an element within an order in the sorted data. And of course, you can solve this problem by first sorting your input and then picking whatever the end entry. But in practice, you can do this faster without sorting because you don't need the rest of the data to be sorted. And why are these important? They will come up in a lot of applications that in practice, people will care about the top 10 element, top 100 element, depending on their application. They will not care about the rest of it in many cases. In subroutine calls, they always come up. I think somewhere in there we learned 2 clustering algorithms, and both of which use that idea of keeping only the top k elements. One was spectral clustering, and the other one was macro clustering. And it comes up more often than you think. There's a whole literature if you even search for it. Some of them call it iceberg queries, and because you want to see the top of the thing as opposed to the bottom of it. Sorting is very important in computer science. In fact, how many of you heard the name Jim Gray? Jim Gray was a Turing awardee who got lost somewhere in the Pacific Ocean. At least people think so. He started sailing from Seattle, I think, and then never made it to San Francisco Bay, which he was supposed to. That was, I think, 10 years ago. And there was a long search effort, both physically and, in fact, people went to Google Maps kind of software, and everyone assigned a little pixel to a person so that they can actually look over the history of this time that he was lost if any ships were showing up. Nothing was found. Nobody knows what happened to Jim Gray. At this point, I think he's pronounced dead, legally speaking. Which is the most likely outcome. But anyway, I'm not even sure if the code is correct, but one of his claims is you would solve more than half of the problems in databases if you just solved sorting. You can just keep your data sorted, and half of your database problems would go away. At least they will be reduced to sorting in some sense. So that's kind of an important problem. And the parallel sorting, of course, comes along with that. Lots of high-performance databases are parallel. My personal interest came from it when my group back in the grad school were developing a parallel version of MATLAB, which most of you probably know MATLAB. Think of it running on a supercomputer. Like you just type in your browser, and on the back end, all your matrix computations happen in the supercomputer. It was really neat until Microsoft bought the company and killed the whole product line. It was really good at the time. And it turned out that, again, just like in databases, if my colleagues, grad school colleagues, figured out that if you could solve parallel sorting, this whole what they call star P, parallel MATLAB, half of the issues will be solved by that. So that's why there was an interest in parallel sorting, and it will come up a lot as a subroutine in other problems. So this is a very fundamental concept. So we'll start with this thing called the master method, and you don't need to learn this. You can find this in the algorithms book Corman-Lyserson, Riverstein-Stein, which helps you solve recurrences. We all learn how to solve recurrences in computer science and discrete algorithms, but you don't need to go back and piece of paper and do this telescoping, hands, prune the elements. There is a very shorthand way of doing this. This only applies to certain kinds of recurrences. Again, for some more complex recurrences, you need more fundamental concepts. These are the recurrences of the kind that you divide your input to B pieces, and there's A subcalls of B size. So basically, assuming both A and B are larger or equal to 1, so B needs to be larger than 1, otherwise your problem is not getting smaller. You're basically trying to find out how this recurrence will solve by just looking at these values. So what you're comparing is essentially, log base n to the log base BA with the Fn, which is the extra cost. So what's going on here? You have a problem of size n. You're calling A subroutines. Each of will work on n over b piece of the data. And just this partitioning cost is Fn. Right? To do the recursive call, you do some sort of computation, and the cost of that is Fn. So by just looking at the cost of that Fn, in order to make the partition with this value, we'll basically partition your problem into 3 classes. So in the first case, if the n to the log BA is larger than Fn, and the more formal definition, it will solve to whatever that is. N to the log base A, you can prove this. You don't need to worry about it. And the other case, when they're equivalent, more or less, it will solve to the, again, n to the log base A, except now they're going to come a polylogarithmic factor, which is log n to the k for some constant k. It's almost, again, n to the log BA, because in computation theory, most of the time people will ignore logarithms. But which exact logarithm is that? Apologies. If your Fn is slightly bigger than n to the log base A by a polylogarithmic factor, so the solution will basically boil down into n times log BA times that polylogarithmic factor plus 1. The power increases by 1. Again, example. So what's going on here? The example is you have t to the n equals 2 times t to the n over 2, and the Fn is essentially that times a logarithm. So this will solve to n log n. Okay. You will see more clearly because we're going to use them. Just we'll refer back to them. And in the opposite case, where the Fn is big, it will solve to Fn. So the simple one is, whichever one is big when you're comparing these entries, n to the log base, log b, a, and Fn, whichever one is big, that one gets to be the solution. If they're equivalent, then the more complicated case in the middle happens, where you have to solve it to, n times log BA times logarithm to whatever that is. This is the factor of this is the factor Fn is bigger than the other variable. You can find this in the books, but don't worry about it. Here's the summary. And this will come handy solving a lot of our recurrences. So let's start with the kth smallest entry, and I'll start with the serial algorithm. So as I said in the beginning of the slide, finding the kth smallest element, the name of this, if you want to Google this and look for Wikipedia, is order statistics, right? Common case is median or some quartiles, like what is the first quartile or is the third quartile, these kind of questions. The example is clustering algorithms use this. So the most commonly known algorithm is called quick-select. How many of you know quicksort? Okay, almost everyone knows quicksort. Quicksort is just an algorithm that performs very well in practice. You select a pivot, and you partition your data that are larger or smaller than the pivot, and recursively call those partitions. It has worst case bad, but almost never happens if you carefully choose your pivots. What quick-select does is very simple. Instead of recursing on 2 branches, you just recurse on the branch that contains the element you're looking for. So that will give you, instead of the n log n average time of quicksort, it will give you a linear time average. It's not worst case. And we'll see an algorithm that does it worst case, which is due to these long list of famous authors. So trivia question. How many of the authors, out of 6 total, so it looks like a little weird, my question, because the 5 guys in the worst case linear algorithm, as well as the whore of the first quick select algorithm. So how many of these 6 guys that have contributed to this problem are Turing laureates? 5. That's actually a correct answer. Is that a guess, or do you know it?
Well, I know 4 of the medians are Turing laureates.
Yeah, I think the only guy who's not a Turing laureate is Pratt.
Yeah.
That's about it. Which I don't know. The funny thing is, almost none of these guys got these awards for that kind of work. I mean, Hoare has programming languages work. Blum is computational complexity, which is much deeper than selection problems. Floyd, again, is I don't think he has gotten this anywhere close. Again, is for programming. Rivest is RSA's R. And Tarjan got it for data structures, mostly. Anyway, but it's interesting that back in the day, pretty much you can get like 5 people work on a single problem, and all of them will end up being Turing laureates. Yeah.
Is the guy called Florider the same person as the one who invented the dithering algorithm?
Which one?
The Floyd.
Floyd invented which algorithm?
It's called something like a Floyd-Stenzenberg dithering for the image processing. It
might be, but I don't know. It's a common last name. For me, Floyd is Floyd's algorithm is, I'm a graph theory person. Floyd Warshall is what comes to my mind, but he's famous for a lot of his work in programming languages, compilers, stuff like that. And I think it's, here's the funny story on this. I believe Tarjan was his student, and Floyd doesn't have an advisor. You can check this out, because he never had a PhD to begin with. I mean, at the time, the computer science department didn't exist, right? They were just looking at the people to hire and figured out there's this smart guy who published the best papers in this area. What does he do? He works as a clerk as a law company. Okay, why don't we bring him and hire him as a professor? You can basically double check and correct me if I'm wrong. But don't you know, not everyone spend that time. There's a lecture going on. So the algorithm is actually pretty clever, and it tells you how most of the algorithm analysis is done, which is kind of backwards. Like sometimes you read an algorithm and you look like random constants in the algorithm. You sometimes wonder, why is it 5 and not 4? That kind of question, I don't know if it happens to you. Almost always, somebody analyzed 4 and figured out that it doesn't come out the asymptotics right. And the 5 becomes the smallest number that gets the asymptotics right. And you'll see an example of this. So those numbers are not random. They're like they're reverse engineered from the solution you're trying to get. Okay, so what you do here is you basically divide your whole, let's say you have a list of n entries, currently unsorted, of course, otherwise the problem will be trivial. You divide this into lists. Each one of the lists are 5 elements only, like tiny lists. Okay, n over 5 lists. So then you sort each list. This is constant time because now you can assume that 5 log 5 is constant. It's small enough. And then you choose the median in each one of these lists. And then you'll do a recursive call. But before I describe it, so I'll tell you what you do with that. So you found all the medians for each one of these 5 element lists. And what you only know is each one of these 5 elements lists is decreasing as you go up, or is sorted, but you don't know the order within these medians. I didn't say anything about this. I'm only going to say now, in the medians list, pick the median. You don't need to sort it. Just find the median recursively. So the problem of solving this thing in n elements, now I'm going to do a recursive call only on this n over 5 elements medians list. Okay, that's my recursive call. And assume you found that median. Call it MM because it's median of medians. right? I haven't said anything about the exact order of these medians. All I'm saying is half of them are smaller than this, half of them are bigger than this, plus or minus 1. Okay. So what's the claim? The claim that the guys that are smaller than this whole list, the rectangle over there, is that list of elements that are smaller than median of medians. And it's correct by construction, right? Because what did I say? This is the median, and all the lists entries within its 5-element list are by definition smaller than median of medians. And I know that all the medians on the left of MM are smaller than MM, which means all the elements that are above that median are also smaller than MM. So this whole rectangle square, all the elements are smaller, or at least just as small as MM. And with the same argument, you can say that this little blue rectangle below is larger than median of medians. Okay, so where do we go from here? What's the size of these lists? This list's size is at least 3n over 10. And you can do it with an easy counting argument. At least you can basically say that if this rectangle continued all the way and only included the first 3 elements of every single list, it would be 6 over 10. And this is at least as big because it also includes the median. So it's at least 3n over 10. And the same argument applies for the size of the C prime. All right. So what does this, why am I doing this, right? It tells me some recursive. Let's come back and summarize this. So I I partitioned my set into 3 different pieces, right, once I choose MM. There's an A, the set of elements that are smaller than MM. This is bigger than A prime, remember. All I'm saying is all the elements are A that are smaller than MM. A prime is some subset of it. But I can prove it's the size of A prime, at least lower bounded. And I can prove the size of C, so which means the size of the elements that are smaller than MM is at least 3n over 10. And the elements that are larger than MM is at least 3n over 10. So I basically bound my recursive calls. So this is the code. You somehow divide the sort, you make the selection. And the important part is this bold-faced comments. Your recursive calls are on at most 7n over 10 data, right? Because for each recursive call, I am basically not recursing at least 3n over 10 elements. And the second recursive call, same. And I'm only doing one of these recursive calls, whichever one has the kth element I'm looking for. This is not 2 calls. This is only one of them will execute, depending on which side of the partition the kth element I'm looking for is. Just like quick select. Okay, so that means my recursive analysis is Tn over 5, because I'm only recursively calling myself on the median of medians. Plus the recursive call is at most 7n over 10, right? And there is an order n of partitioning cost, because I somehow need to touch this data. Okay. Any questions? Every year I think I can explain this better, but it's delta improvement. Okay, it's clear? No.
Yeah, actually, how did you get a median like in O and I?
So which so you're talking about ON time. I actually didn't find the median yet. Oh. I just recursively delegated that problem. Right, so I basically said, I start with this whole data, and I am delegating the median finding problem to the recursive call on the n over 5 list. It will eventually find it based on the induction from the base case. And assuming that I find it, now what is the cost of figuring out what part of the data lies before this on the smaller side of MM versus what part of the data lies in the larger than MM side? That's the cost of ON. It's not the cost of finding medians. So in recursive algorithms, you assume that your recursive function will find that element, and you have to prove it with induction, but so that's not the cost of finding the median. It's the cost of partitioning the data, the plus order n. Okay, how do we solve this? So the first thing we understand is, we sum up the numbers. It's actually t 9n over 10 plus 10 plus order n, right? You just sum up the two t values there. You go back to what we showed in the beginning of the lecture. So now you're comparing n to the log BA. What is n to the log BA? It's, it's less than or equal to order n. It's asymptotically pretty much the same order n, but it's less than or equal to. So it's going to be equal to order n. Whichever one is asymptotically larger will be the solution of the master method. That's all. Now you can ask me, why 5 element lists? Why not 4 element lists? Like when we chose these lists, why each one of these lists have 5 elements?
Does it have something to do with the A and B value?
Yeah, clearly, right? So first of all, you don't even need to look at the master method. You can see the main problem if that call was not n over 5, but instead it was n over 4. You run the numbers, you'll see that your recursion will not be shrinking this, your recursive function will not be making progress. You'll be continuing to recurse on the same size data. So 5 is the smallest data that makes sense. And why not something bigger? A bigger will fix it too. Bigger is okay, more or less, I think. I'm not actually sure, I haven't tried. Maybe even 6 might be an issue, because then 6 will increase the second term here, right? Because the sizes of the lists determine how much you can get rid of at every recursive call. If you have too many lists, then you're not getting rid of enough elements. So the 5 seems to be the right number that gets this thing to be correct. Anyway, actually this is a parallel selection class, so we haven't even come to parallelism yet. But this method will be a nice shoe-in to the parallel case. And I'm spending this time because last year I gave this lecture on 2/3 of the lecture time. And I said, well, okay, I'm either going to add more stuff or I'm just going to spend more time. So we're spending more time, not because there's not a lot of literature. I can talk about literature for days on parallel sorting searching, but some of these algorithms are mostly engineering efforts. You basically have fundamental concepts, and then you have to get them competitive. Since this is an important problem, people actually have standard benchmarks that they compare themselves against. You have to engineer them to the point that you don't call any of the pure algorithms, you just do combinations of them. They have different trade-offs. Anyway, now you know why you have list of 5. Let's get to parallelism. So, can we do parallel selection with median of medians? So let's say we partition the input set to processors. Each processor has n over p data, right? And then we say, let everyone compute its own median, and then somehow we're gonna recursively find median of medians, and discard some elements and recurse. I haven't analyzed this at all. Like, let's assume that's some sort of idea, right? Well, the problems with that is you don't know how things are distributed initially. So once you started recursing, you might create a lot of load imbalance. So let's say every element has, the list I'm sorting is 1 million, and I have 10 processors. Everyone gets 100K elements. And they all find their local medians. Somehow, with a method that I haven't described, I found the global median and partitioned each processor's data into 2 groups, and they will continue in their subgroup, right? Now, nothing in this tells me how these local lists are going to be partitioned. In one processor, they might be like recursing only a leftover of 5 elements. The other might be 95 elements out of 100%. So that will create a significant load imbalance, and you would require data redistribution to correct the load imbalance. But the good news is you can analyze this data distribution and say that asymptotically it's not hurting you too much. You can get a fairly complicated algorithm that will give you, at least on the computation side, which is almost optimal. So N is the data size, N over P, linear, plus K. K is the number of elements you have to output anyway, so it's okay. And on the communication side, it's not too bad either. There's quite a bit of log factors, but it's okay. So, and you can find this algorithm here. It's quite complicated to describe, and in practice, the analysis is hiding quite a bit of data exchange. So here's a simpler way to do it. Without data redistribution, without explicit load balancing. So instead of basically dealing with the load imbalance by shuffling data at every recursive call, what we're going to do is we're just going to deal with it algorithmically. We're going to let processors be load imbalanced, but at every recursive call, I'm going to, instead of choosing explicit median, I'm going to choose something called a weighted median. So if a processor has more entries than the other, then its median will have a higher weight when it's chosen. Okay, so that's basically the idea, and it's going to make it come right in the end. So these are the references, and I'll describe this in detail. The code is, again, not that particularly nice, but it's not different than what we've seen. The reason this code is here is to show that it's almost identical to the selection code that was out there. So, in all of the recursive serial selection codes, calls are the same, except now they're called parallel select. And the only two differences here is there needs to be a couple of MPI calls to figure out the global medians elements, what the median is. And instead of finding the median of the medians, you find the weighted median of medians. So that's only the two differences there. Okay. Okay, so the analysis. So the more important thing is, again, the highlighted comments at the bottom. So now instead of doing 7n over 10 recursion, I'm going to do 3n over 4 recursion. So these things, the sizes of the recursion is on the data set at most 3/4 of the initial data. So where does this number come from? Okay. Unfortunately, I can't draw you a rectangle because weighted median is a little harder to visualize than the median. But we can do it algebraically. So what's the definition of weighted median? You can think of the original median definition as all the weights equal to 1. So, oh no, all the weights equal to 1 over n, right? So you give a weight to every element on a list of n elements, and each weight is 1 over n. The exact median in our original definition is you basically find the location where half of them, 1 over 2 of those weight sums are smaller than the element we chose. That's the median definition. Now what's only changing here is instead of 1 over n, I'm going to insert arbitrary weights. The weights of those should sum to 1, but that's okay. So there's just a definition. It just tells you, like, you can adjust median selection by using weights. Now, instead of using, where will the weights will come from? They will come from the elements in each processor's local batch. Okay, so what's the notation in the previous lecture, previous slide? Okay, so this is the thing that I should write down on the board so that I can help with this. Is that what it is? Okay. So let's say you have multiple processors. Each one of them has a different median, right? I'm just reminding you where the numbers are coming from. so that when I change the slides, they stay. So M0 is this guy's local median. M1 is this guy's local median. M2 is this guy's local median. M3 is this guy's local median. And there's a local median for every processor, okay? So that's where the MIs are coming from. And I'm gonna set a weight for every one of these lists. So this is the position of the data after some unfortunate recursive call that left different sizes of lists in each processor, right? Initially, everything can be balanced because I can explicitly balance them. But at some point, due to my recursive call and the global median I chose, some processors will have less elements left to recurse. Some processors will have higher elements. So how can I deal with this is the heart of this algorithm, right? So again, go back to the weighted median definition. And the number of elements in each one of these lists is, this one has N0 elements, this one has N1 elements, N2, N3. So the total number of elements is the sum of NIs for all processors, I equals 0 to P, right? So we know by definition at each processor, the number of elements that are less than MI is, this is less than or equal to N0 over 2, this list is less than or equal to N1 over 2, and so on, again, by definition. And all of these elements are smaller than the median of the medians that are, half of those are less than the median of medians by definition, not all of them. So how much am I getting rid of by this concept? Okay. Again, just to remind you, what is big M is the weighted median of these medians, M0, N1, MP. Okay, that's again not in the slide anymore. So big capital M is the weighted median of those, and by definition, all of these elements, N0 over 2 elements, N1 over 2 elements, and N2 over 2 elements, the half of those, the top elements, are less than or equal to capital M by the weighted median definition. And if you sum up their sizes by the definition of the weighted median, because you're going to be scaling them, you'll see that n over 4 of them are exactly in that group. So you can basically toss n over 4 of them at every recursive call. And same argument can apply to the case where how many of them are larger than that. It takes a while, but you have to basically write down this summation. You basically say n0 over 2 plus n1 over 2 times the weights of those that will come from. No, you don't need to do weights. You'll just see that the sum of those elements will get rid of n over 4 elements. Exactly. So either way, by just weighting the lists weights by the list size, I'm able to get rid of half of the elements. If you don't care about algebra, all you need to think is if you have to basically choose the weight of a median on a larger list to be higher so that you can make this argument. That's all the adjustment we're doing. And then once you have that n over 4 elements disappearing, now your recursive calls become, communication is 3n over n plus the cost of data distribution, and the computation becomes again, what is going on here? Okay, so this is what happens when you solve this. Let me see how we solve this. Number of recursive calls is log n.
3n by 4 elements being redistributed at every...
No, we don't redistribute. That's a great question. So I haven't analyzed the computational cost. This is only limiting the communication cost. There will still be load imbalance in the sense that what I'm not guaranteeing is the cost of partitioning this list. I'm not guaranteeing that it will be load imbalance across processors. So it might be a problem with load imbalance there. But what am I guaranteeing is the recursion globally reduces the remaining data set so that it will finish in log n steps. That's all I'm doing. There might still be load imbalance within each processor, but the overall computation time will not be affected too much. You might be wasting processors, but the balance will come out correctly. Okay. I see what's going on now. Now I remember what the algorithm's trick is. So this actually will not directly solve to the correct numbers if you continue the recursion all the way to the bottom. Simply because there's way too many recursive calls, log n calls. Instead, what the algorithm here does is when the total remaining number of items is order n over p, meaning that it's reduced by a factor of p, it stops the algorithm and gathers all the data into a single processor, okay, and then solves it. Fine. And why n over p? Because to go from n to n over p, instead of doing log n recursive calls, you just need to do log p recursive calls. And that helps to come out the analysis numbers right, the asymptotics right. So now from log n, your number of recursive calls becomes log p, okay? And there is an extra cost to gather. So the communication cost, instead of having a log n factor, it now only has a log p factor. So instead of these log n's, you have log p factors, but the extra cost to gather showed up here as n over p. But that seems to be fine because n over p is what's expected anyway from a properly scaling algorithm. So the only time that this will not scale if is p times log p is larger than n over p. And that's a somewhat of a reasonable number because for p number of processors to be really high is a rare case. This is going to guarantee some weak scaling for large n. It's not going to guarantee strong scaling. And the computation, unfortunately, is this guy, n over p times log n. And there are two reasons why this is. Because one is related to your question. I'm not getting rid of the local lists. So I can't prove that the local list size will shrink. So n over p can be n over p throughout the whole computation. That processor might be unlucky and might be choosing a bad pivot all the time. So I'm not really getting the advantage of shrinkage in general. And the second reason is there's a local sort anyway, so it doesn't matter. The local sort is n over p times log n over p, which is more or less the same thing. So there's not too much reason to optimize this step.
So that local sort is coming because we try to break down the computation factor to log p.
Yeah, the communication factor.
Communication.
Yeah, we don't want this p times log n because the dependence on log n in the communication cost is it doesn't make the weak scaling numbers come out right. You want your weak scaling to be somewhat independent of that n number, log n number. So that's basically the main reason. It has to do with basically something called an ISO efficiency curve. You try to show, okay, in order to keep my parallel efficiency constant, how much I should, every time this is a concept we probably never saw. So one of the questions parallel algorithm designers ask is to keep parallel efficiency constant, meaning that as I add more and more compute power, I'm not wasting my larger computers. How should I increase my problem size? A single processor is solving 1 million, let's say. If I'm solving the same problem, 1 million element sorting problem with 1,000 processors, I'm probably not going to get the same efficiency, right? But there is a function that relates to this. If you want to keep the same efficiency, you should increase your problem size by a factor of blah. and that blah is a function of the number of processors. So you say that, and if it's usually order P log P, it's nice. Because you can say that, P is great. When you double the number of processors, you double the problem size, which is meaningful, and then you will get perfect efficiency. That's good. But if your ISO efficiency number has this P times log n, which is like this, then you're in big problem. Why? Because this is dependent on both the problem size and the processor count. So, and they are both in the nominator. They're not, N over P is okay because, if one of them goes up, the other one cancels each other. Here, as the question becomes, as I increase P, how should I increase N so that this will stay constant? There's no answer to that. Both of them are multiplicatively forcing each other to go up. So you shouldn't be increasing N then because, but then that's the only way to keep the parallel efficiency constant. So you will be in big trouble to have both N and P as multiplicative factors to each other in the communication costs.
But parallel efficiency here is coming at the cost of overall extra work, right?
Yeah.
So the overall runtime might, like for example, if I add 2 processors versus I run the linear time median on 1 processor, I run this on 2 processors and the linear time median on 1 processor, they might end up finishing the same problem size at the same time because this is doing extra work.
I mean, the parallel efficiency is really the ratio of the time you could solve this problem in a single processor to the time you solve it in P processors times P.
But for here, the time for single processor would go up to n log n.
Yeah.
Right?
Yeah.
But the best known algorithm is n. On a single processor, if you use the quick select.
Yes. So that's the comparison I should be having. Yes. You're talking about the computation cost down here in terms of comparison. Yes, there is always a log n impact to your efficiency. Yeah, that is right. That's almost for this algorithm. There's more complicated and better algorithms, but implementing them, I don't think anyone actually even did that. Just to recap what's going on in the selection part. Do you remember the parallel graph algorithms where we solved a couple of problems like maximal independence set with randomization? You just tossed coins and picked up vertices based on how they picked random numbers compared to their neighbors. And here randomization helps a lot, and it creates much simpler algorithms. Maybe next year we're going to talk about those because they're actually much simpler to describe. They're not simple to analyze, but they're simple to describe and implement. Their bounds are not exact, they're probabilistic bounds, but they'll be fine in many cases. Lots of randomized algorithms. Questions? This was much more board work than I hoped to do, but I don't know if it was helpful or not. But let's come to sorting, the second part of this lecture. And I'll start with a simple one, merge sort. And this one has a lot of nice pictures, so it's hopefully not going to have a lot of complicated math. Merge sort is one of the order, n log n sorts, which is, in the comparison model is optimal. It usually loses to quick sort in practice, but it has a nice property. It's in place. Sorry, it's not in place. That's one of the reasons why it actually loses to quicksort. Quicksort, you're given an array, the output can be directly that array as opposed to creating a temporary space. Merge sort will not do that. Merge sort will need an additional array to move items back and forth. And that's potentially why it's actually slower. It's creating more memory traffic. This is the code for merging. You don't even need to think about it because you probably have implemented it enough times, or there's a merge function in every library like STL merge, okay? And unnecessary merging illustration. And the time to merge is linear, right? You just scan both elements. So parallel merge sort is, this is updated. What basically you need to do at merge sort, if you remember, is you will recursively call merge sort until there's only one element left in each list. And then after recursive calls, there's a merge. And this is actually a very great way to describe recursion. I sometimes, for undergrads, I just go to the compiler's debug session and show how the stack is going and then collecting itself back. Right, so what's going on? Recursive call first, recursive call second, recursive call third, and then from now on, all the rest will be merge calls. First merge call, second merge call, third merge call. This is actually what I described as both applies to serial algorithm and parallel algorithm. The only difference between serial algorithm and the parallel algorithm in OpenMP is this red text. And in fact, this red text doesn't need to be that long. The only reason it looks weird is because of OpenMP syntax. Remember, OpenMP didn't have tasks until version 3. So the task concept was retrofitted to OpenMP. That's why you have this, first you create a parallel region, then you create a single region, and then you task. If someone designed this from scratch, they would only be task calls. Right? But in OpenMP, you cannot create a parallel region without the parallel pragma. But you can't create tasks from different processors, so you have to call single. It's a syntactic, crap. But don't worry about it. The other systems like Silk will just let you put a spawn in front of your function and will be done. And there is no task wait because the closure of that parallel region will be an implicit synchronization anyway. So I didn't put that. So, so what is potentially going wrong here? I can recursively call merge sort. Fine. Right? And then, so what's gonna go wrong here if this is my algorithm? And I expect parallel performance.
All the merges are sequential?
Yeah, the merges are sequential. So once you analyze this, what you're going to get is work is 2 times n over 2 plus order n. You don't even need the master theorem to get the intuition why this is going to be slow. But if you use master theorem, you will also get that the work is fine, meaning that you're not doing anything more. But the span, do you remember what span was? The critical path of the algorithm. Meaning that if I gave infinite processors to this problem, how long will it take to run? Or what is the longest dependency chain in the algorithm that cannot be parallelized? It's also called critical path, or depth, or span. Unfortunately, there's 3 names of this. Depth is, I think, useful because you look at the recursion tree and what's the depth of it in the worst case. And the depth recursion is, you're creating a problem n over 2. If you have enough processors, there's not going to be a factor in front of it. But as you said, the merges are still sequential. So if you solve it with master theorem, you'll see that your span is order n. And that will leave you very little parallelism. This is the work, this is the depth. Your parallelism will be only log n. So you can only get speed up to log n. And that's not a big number. So that's not a good algorithm. So what we need to do, we need to parallelize merge. How do I parallelize merge? This is basically the only cool part of the merge sort algorithm. And it's actually very simple once you see it. So assume you're trying to merge 2 lists, and without loss of generality, one of them is at least as large as the other one, larger or equal to the other one. But at some point during the recursion, they will go out of balance, and this will happen. So one of them will be at least as large as the other one. Pick the larger one, right? So, and find its middle entry. This is not a recursive call. These elements are already sorted based on your merge sort function. So you're just trying to merge elements that are already sorted. So once you pick the middle entry, this is constant time, then find that middle entry in the smaller list. Do a binary search, right? Just find that element in the smaller list. You did the binary search. Now what can I do? I can recursively call these sublists, right? I know on the pink B list, everything on the left of whatever returned from the binary search is smaller than that element. And same for all the elements on the left of that MA in the first list. So basically these two binary merges, these two parallel merges are independent of each other. Once they return, I can just glue them together. Okay? So what do I need to do to prove that this algorithm is actually better than sequentially merging it?
So at the cost of log n extra work, we reduce the work by n by 2 by doing that in parallel?
I'm not really reducing n by 2 yet. That's the issue. So I haven't proved the size. So there is no proof yet that says I am reducing enough elements. I'm tossing enough elements by this procedure. And that's what we're going to do. So all I know from this for now is I am at least not recursing on half of the elements in A. But this doesn't say anything about the size of the elements in B yet. All right. So all I know from this picture is, I think what you can say is 1/4 of the elements are gone. Right? Because A is at least as big as B, and 1/4 of the elements will be gone because I'm getting half of A. All right, but is that enough? When your question?
When you say 1/4 the elements are gone, you mean within one subcall, right? Because you still need to do both sides.
Yes, exactly. And that's why getting rid of 1/4 elements, sometimes there is no magic number in about 1/4. It depends on how the recursion, how your recursion is. So your FN, the cost of recursion, matters. In the previous case, when we were describing the parallel selection, 1/4 was enough, because our work to partition that was large enough. In this case, it might not be enough. So let's see. That's exactly what we talked about. You get rid of 1/4. So each merge call is at most 3n/4. So all that changed is instead of so this is the parallel merge call. This is not the merge sort, this is just the parallel merge call, and it's exactly in code what we've described. You pick the larger element, find its middle entry, binary search it on the other one, and do recursively parallel merges. Okay, so what's the span? The span is easy. Write 3/n plus log n to find it, the binary search. Let's say I didn't parallelize binary search. And so this is the nice, remember, case 2 of master theorem applies here, which is the nicer one. So I look at n to the log BA, so it's 1, okay? What about Fn? Well, Fn is larger than this. Since Fn is, but they are to the polylogarithmic factors, they are within each other. So what do I need to do? I need to basically increase the power of log n, and multiply that with n to the log BA, which I will get log square n. Because these are polylogarithmically the same, n to the log BA and Fn. So I just increase the power of log n. Fine. Span is this, which is good. It's a low depth algorithm. In fact, we don't teach theory of parallel computing, but for people who teach it a lot, the holy grail is to get polylogarithmic depth. In fact, there's a whole class of parallel algorithms called NC, which are the algorithms that can get polylogarithmic depth. So there's complexity theory of parallel algorithms. And the funny thing is, I always thought NC is something as cool as like NP, right? But it turns out it's as simple as Nick's class. And you can see who Nick was on Wikipedia, but it's not like non-deterministic polynomial time kind of thing. It's just Nick's class. And then there's randomized Nick's class, whatever. So the work is tricky, because what's happening is, as you pointed out, the span is only one-sided, but the work is two-sided, as you said. Span meaning that if I have lots of processors, infinite processors, the cost is the maximum of them, and that's 3/4. But for the work, I have to recurse both sides, and I have to consider both sides. So there is some alpha that I don't know of, right? So I'm calling myself twice. One of them is alpha type n, the other one with 1/alpha times n. And all I know about alpha is it's somewhere between 1 over 4 and 3 over 4. I don't know exactly what this alpha is, right? So, and then the binary search is the same. This is kind of tricky, but I can claim that it's linear time, and I don't even know if I want to do this, but you can basically make a claim and prove it by induction that that's the case. And the slides have pretty much all the details to do that. You basically make the claim that in the inductive hypothesis that the solution is linear time, C1k minus C2 log k for some constant C1 and C2, and then you'll solve it for C1 and C2. It's not going to get nice. And then you can basically prove that you can choose C1 and C2. There are some constants that will make it linear time. So the solution is the work is linear time, as we expected, and the span is logarithm square of n. So there is enough parallelism here. If you want to imagine what's going on, if you're merging 1 million elements, this is, what is the log of 1 million? Log base 2? No? So,
20.
Yeah. And why? Because 2 to the 10 is? 10, about 1,000. So 2 to the 20 is 1 million. So that's easy. I mean, whenever you do logarithms, you can think of it that way. 1,000 is 10, and it's additive. So million means 20. A billion would be 30. So it's basically a million divided by 20, which is still a huge number. You can scale this pretty well. Even strong scale it well. Of course, there are constants. So parallel merge sort becomes exactly the same skeleton, but instead of calling merge serially, I'm calling the parallel merge function I just developed, right? And the work of it is log n. By proving again with the case 2 case, because they are polylogarithmically within each other. So I'm just adding a logarithm for that. And the span is interesting. Span is, n over 2 cost from the recursive merge plus the span of the merge that I discovered, right? So this is n cubed because again, case 3, they are polylogarithmically within each other. I just need to increase the power of logarithm. So what happens? Work is logarithm times more, span is logarithm times more. Same parallelism. Good. So the merge sort is over. Then I will move to distributed memory. But before that, I should say a couple things. Fundamentally, there are lots of theoretical sorting algorithms in parallel. Some of them are esoteric, that they fit the architecture very well. There's some concept called a sorting network. That's like a specialized network that does comparisons, but that only made sense for the architectures. For standard distributed memory machines we have, with standard computers and a fast network, there are really, at the moment, 2 algorithms that live. One of them is based on merge sort, but instead of this merging 2 lists, it merges multiple lists. Its main primitive is merging p lists at one time. Okay? And unsurprisingly, the version in distributed memory machines, the competitor is called sample sort, and it's the same idea. Instead of doing a quick sort with a single pivot, you'll now do a quick sort with p minus 1 pivot, multiple pivots. You see the analogy here. Basically here, we're able to call recursion really easily in shared memory. So the algorithm I described, the merge sort algorithm, is really a shared memory algorithm. It creates parallelism itself as it goes along. In distributed memory, this doesn't really work very well because it's not a, it's a SIMD machine. The data is already distributed. So there you have to basically find a way to merge P lists as opposed to 2 lists. And the main primitive becomes that, multi-way merge. And similarly for quicksort in distributed memory, it's a generalization called sample sort. So then instead of choosing one pivot at a time, you will be choosing p minus 1 pivots. And that will split the entries to each processor. We will only see one of them, sample sort. They have trade-offs. Sample sort's bounds are usually better, but its communication can be higher significantly, depending on the problem size. So the state-of-the-art algorithms do two things. One of them, they switch from one algorithm to the other at some point on the process. And the other thing they do is they do something called a multi-level optimization, which I won't describe. It basically tries to localize the computation to a group of processors. Like instead of working directly on P processors at every stage, it tries to find, after the first stage, it creates basically two P over R problems, R size. Think of like, square root of P, you can choose that. So after the first recursion, you basically try to create sub-problems. Each of them are running on square root of P processors, and there's square root of P sub-problems. You can tune that square root of P to be something else, but you're trying to create a multi-level algorithm. But those are the practical ones. So let's see what they're based on. They're all almost based on this thing called the sample sort. Before I describe sample sort, I'll describe bucket sort, because it's very easy. Let's assume your input is uniformly distributed in integers or floats. In this example, let's say it's any range, A to B, right? If I know they're uniformly distributed, all I need to do is divide this range into equal P pieces and say all the elements that are within the first 1 over P piece of this range, go to the first processor. The second 1 over P of this range, go to the second processor. Think of this range to be, 1 to 1,000, and you have 1,000 processors. All the elements with key 1 goes to the 1. If they're uniformly distributed, everyone will get the same number of elements. But that's a little bit of a too strict assumption, right? The data is usually not uniformly distributed. But it gives you a good idea where to start with these algorithms. In fact, another name for these kind of algorithms involve something called the histogram sort. You can think of bucket sort as a histogram sort for a trivial distribution, a uniform distribution. You just look at the histogram of the data, it comes out uniform, right? And then it's easy to distribute that. A generalized histogram sort is try to quickly build a histogram of data distribution, and then basically looks at that histogram and says, okay, based on these histogram entries, I need to assign the first 2 entries, the first 2 histogram columns to the first processor, the second 3 of the second processor. So you basically choose based on looking at the histogram, which is some sort of a summary of the data distribution. This one is if your histogram is as simple as uniform. And then if you do this, the runtime of your algorithm is not bad. Again, there is no parallelism in this description yet. I just said m equal size intervals called buckets. So that's what it gets. Parallelizing this idea is really simple. You just choose number of buckets to be the processors. Essentially, lots of words that I already described. You go over your data, you choose the bucket, you do a big all-to-all, and then everyone will locally sort the output, done. Load imbalance might happen if your data is not uniformly distributed, but in general, you'll be fine. But let's come to real non-uniform distributions. So this is probably the most accessible but not trivial description of sample sort that we're going to study. It's from a paper called Parallel Sorting by Regular Sampling. Okay, it's quite old, maybe 2 decades. As I said, generalization of quicksort. So instead of basically choosing ranges of values, you basically need to find some splitters, right? So like good pivots in quicksort language. But how am I going to find good pivots? So that's the thing. Like I described, like a histogram idea would work. This is something like the histogram idea. You're basically trying to find good pivots. So the algorithm starts by everyone basically locally sorts its range. Let's say the data is distributed. Everyone will locally shortest range, and then they will choose samples regularly spaced. And I highlighted these two words. One of them is evenly spaced, the other one is regular sampling. This is not random sampling. So this is, you sort your local input and you regularly sample it, meaning that you choose the third element, sixth element, ninth element, right? There is no randomness here. You choose exact elements. But everyone is choosing more elements than they need. If you think about like m equals p, then instead of choosing one pivot per processor, every processor is choosing p minus 1 pivots. So there is, you will have p times p minus 1 pivots in total, more than p processors, like by a factor of p. So here's the picture. It's actually pretty nice. Let's say p0, p1, p2 has been distributed these sets evenly, more or less. They locally sorted their inputs. Can you see that, or is it too small? Okay, so then they just chose the every third element as what we call the regular sampling. And in fact, this picture works because, again, we need to choose two pivots because P is 3, a number of processors is 3. So everyone chooses two pivots. And then these samples are combined. In this simple algorithm, they're combined in a single place. Single processor receives these P times P minus 1 elements. Don't ask me, there's better ways to do that. You can recurse a little better until it gets small enough. But in this basic case, let's say it's all gathered into a single processor, okay? So this is combined somehow. You don't need to sort it again, you can just merge it. P-way merge is fine. See, because they're already coming sorted from the processors, because the samples are regular and samples are from locally sorted inputs. So all this, what you're getting from P0 is already sorted. What you're getting as P1 is already sorted. You just need to merge them. You just combine them and then find global splitters and then redistribute the data based on that. So what do I mean with global splitters? Okay. Let's talk about it a little bit more. So then how do you choose the final global splitters? You do the same regular sampling, right? So you received m times m minus 1 elements, and you will choose every m over second element. So m over second element, m times m over second element, so every mth element, sorry, not every m over second, but starting from m over second. Make sense? Everyone sent you m minus 1 elements. You just regularly sampling the output. The distances of these are the same too. So both in the local sample selection and in the global sample selection, you're basically choosing every mth element. So what's the proof basically? The proof is that each processor, at the end, if you choose the final splitters like this, what do I mean with splitters? You basically tell the final processors that these are the global splitters. If I'm choosing every mth element from this global list, I'll be left with m minus 1 global splitters. So all I'm saying, processor 1, anything smaller than the first splitter is yours. Processor 2, anything that's larger than the first splitter but smaller than the second splitter, it is yours. So that's basically, I'm broadcasting everyone. And what people do is they look at their original data. They say, okay, anything that is smaller than the first splitter, I'm going to keep. Anything else, I'm going to distribute to whomever I need to distribute. So they'll do an all-to-all after they look at the global splitters. So all I need to know is in the final assignment, how many entries each processor gets. And there are 3 cases. The first processor case and the last processor case are a little special. But the middle processor case is the most complicated, so I'm just going to describe that one. If you're one of the processors in the middle, not the first, not the last, you basically get entries that is in this range, right? Anything that's larger than I minus 2m plus m over 2 and less than or equal to I minus 1 m plus m over 2. Do the algebra, this is what I described exactly in words. The i's and indices might be a little tricky. Yeah, I might have been making an I minus 1 error there, but that's, in general, it's what I described. And the nice thing is you basically look at what's the upper bound and translate it into instead of I minus ones, it's what is it in terms of looking at the end of the list. It's m minus I. So you basically see, your lower bound is larger than these many elements by construction. And where does this come from? It's actually pretty simple, because this is the I minus 2 m times m over 2 of the splitter selection. This is its location within the m times m minus 1 splitters. And each splitter entry is bigger than at least n over m square elements. By the way, we chose samples. Sorry, this actually made a mistake here. Not a mistake, I didn't describe this. So each one of these entries, no matter where they are, each one of these splitter candidates we chose is larger than n over m square elements, by definition. Make sense? I mean, this whole thing is m, sorry, this whole thing is n, and this is n over m here, right? And then each one of these regular samples is at least as big as n over m squared. In fact, only the first element is tight. Everything else is significantly bigger than, everything else is bigger than way many more entries. But every single entry in the splitters initial list is larger than n over m square entries. And in fact, if you don't want to think about m's, let's say n over p square entries for m equals p case. Okay, so good. So I know I am bigger than these many splitters, and each splitter is bigger than n over m square elements. So I just multiply this. Good. And then I can make the same argument for the UB case. Okay, for the upper bound case, I am also smaller than these many elements on the right. So what do I gain? This is pretty bad. I look at this. I'm responsible of these guys. So this is my lower bound. This is my upper bound. I just said that I'm larger than these elements. I'm smaller than these elements. Now all I need to do is n minus LB plus UB. This is not UB. This is the length of this is UB. The length of this is LB. So if I know this value, this is what it is, at most. Right, so it's less than or equal to this. This is larger than or equal to larger. So basically, once I do this algebra, 2n over m. Great, what did I accomplish by this math? Anyone following?
Almost balance.
Yeah,
to a factor of
exactly. The worst case load imbalance is a factor of 2. In fact, since my argument was so weak, all I said was that every one of these m times m minus 1 splitters is larger than 2n over m. In general, they're much more tighter than this in practice. But I'm not going to go into more complicated algorithms. The worst load imbalance is 2x. In practice, way better than that. So by just doing regular sampling, which can be described in a single page of paper, I actually get a good sample sort. So things that can go wrong. The size of this initial sample set, candidate sample set, is, if I choose m equals p, is p times p minus 1. You should basically think, let's say you're trying to sort in 2,000 cores, 20,000 cores. What is p times p minus 1? It's 5 gigabytes. So it's really hard to gather this thing in the whole single processor, right? There are multiple solutions. You can basically, instead of gathering this in a single list, you can call recursively yourself and work on smaller input data sets. That's one solution. You have to have a good sort that scales on smaller number of data, and some of these engineering papers actually do that. They basically first develop a building block that's good enough sort. It might be inefficient, but it doesn't matter, because once you do the recursive analysis, the cost of the recursive call doesn't have to be the best possible. It just needs to be good enough to get the asymptotics right. So they use that call. Or you can find the exact median, which is possible, and then recurse your problem into 2 sets. Once you do that, your p goes down by 2, and your p times p minus 1 goes down by a factor of 4. So your memory storage problems go down. When you just do 2 pieces of recursion, your 5 gigabytes problem will become 200 megabytes problem very quickly. But finding the median might be a little tricky. We know how to do it though. So you just need to call what you learned in the other lecture, find the median, split your processors into 2. They will not talk to each other. You'll create an MPI language, separate communicators. Go. But you can use exact splitters, lots of other ways to do that. Here's a complexity analysis that I don't really like. So, this is directly from the original paper. I didn't play with it, but I'll tell you why it's missing some entries. So the internal sort, we know that's easy, right? Every element had n over 2, so it's n over p elements, n over p times log n over p, okay? And then you need to choose regular samples. You can do it in order p time if you're choosing p minus 1 samples. The all-to-all broadcast is p squared. That's fine. But here what this analysis gets a little funky. One processor will get p times p minus 1 samples and will sort them. It's p square log p, fine, because logarithm of p square is the same as logarithm of p. And then, see, there is no beta and alpha here. Yeah, go ahead.
Isn't that just a merge operation?
Yeah. In fact, first, that's the notion issue.
That's a p square element.
Well, actually, if it's a merge operation of p elements coming from p sources, it's the same, I think. Yeah. So you don't need sorting or merging. In this case, doesn't give you benefits. If everyone wasn't choosing order p elements, it would give you an element. Since the size of each set is the same as the number of lists you're merging, the asymptotics came the same. But my main issue is not that. My main issue is the cost of broadcast, is order p squared times the latency. Right? The factor there is way higher than the internal sorting factor. So this is not analyzing communication. This is just analyzing the operations you do. So the cost of all-to-all broadcast has the latency factor, the alpha, remember? And this paper doesn't actually talk about communication cost. That's why it's ignores the all-to-all because it says the internal sorting is already larger than that. But in practice, the all-to-all will take much more time than the internal sort, of course. But if you don't use the alpha-beta model, the exact cost looks like this. And I said why this formula has some issues, because it's not including the latency cost of all-to-all as a separate term, which will have alpha times order p squared. And there are 2 algorithms here. They do a lot of engineering work to make these kind of algorithms go fast. Hike sort I put there. It is a multi-level algorithm that I described. It basically creates groups of processors that recursively do, actually sample sort. It says quick sort, but sample sort is the generalization of quick sort. So that's probably the best algorithm in its class to describe, if you're interested in kind of sorting problems. And it's actually, code is online. If your problem has any sorting needs, you can download HikeSort. It runs on Cori. We've tested it because we needed some scalable sorting code in our research. And I think that's about it. Questions?
You have those algorithms that do you have a recursive step, and then within them you have another parallel recursive step. Are those actually used companions? Because it sounds very difficult to
Sorry, what ended up happening is, where is the microphone? Does anyone have the microphone? Yeah, can you pass? Because at the same time, the people outside the room was laughing. Go ahead, please.
Okay, so I don't know if this is on. I guess the question was if you have like a parallel algorithm that's recursive, and then like within each recursive step you have like another parallel recursive step, is that like practical to use? Because like you have to like, sounds pretty difficult at least.
Well, I mean, it depends. The question, I think, is, now the microphone is there. I don't need to repeat it. How do you do multiple recursion? Like in shared memory, this is usually trivial because the runtimes like OpenMP's tasks and others will take care of it if they're implemented correctly. What you're describing is really nested parallelism. Like there's a parallel region and inside there's a nested parallelism. So it's a very well studied class of scheduling problems that work very well in shared memory. In distributed memory, usually schedulers don't work very well because they have to coordinate with each other and it's very expensive. Distributed memory recursion is not really done like creating more children to each other, but most of the recursion is done as the way we described. You recursively call, every processor stays within itself in its recursion, meaning that there is no new processes that generate it. Think of the median of medians algorithm. So your whole recursive concept is, I am locally recursing on half of my data. So, and there you can think of it as just the same recursion in a single core. You're just calling another function. Everyone calls a recursive function. They coordinate. So there's no issue of scheduling that thing in distributed memory, and that's how usually recursion is done in distributed memory. Instead of starting with a single big problem that it runs on a single processor and then starts running with 2 processors, 4 processors, 8 processors. In distributed memory, it starts with everyone is active, and all the recursive calls are just referencing their own data and their own stack. They're like conceptually a little different. I'm not saying you can't implement shared memory like recursion with a single control and then creates more children, but that doesn't really work very well with existing distributed memory systems. But there's no problem with nested recursion. In general, I have seen practical issues with the MPI library. If your recursion stack is high enough, somewhere in there you might exhaust some of the resources. Like there's fixed numbers, like the sys code can create at most 1,000 communicators, let's say. And if your recursive function is deeper than that, and it's for each call is creating multiple communicators for separate communication steps, at some point this thing will crash. We'll say, the internal number of communicators exceeded maximum, something like that. But it's not a fundamental reason, it's just nobody expected you to write the code like that. There is no fundamental limitation of doing recursion in distributed memory. You just need to make sure to minimize coordination between processors and try to keep your recursion within the same group. Questions? I mean, the general answer. 2 types of recursion in distributed memory that are very widely used in practice. One of them is you basically recurse. You not only split your data, you also split your processors. Think of the find the median in your data and then swap the entries in the smaller than and larger than the median and call the recursive step and half of the data with half of the processors. Right? So you're not only shrinking your problem size, you're also shrinking the number of processors that are working on that subset. So for that, you have to create a smaller communicator in the MPI language, and then they will communicate within that communicator. Or the alternative is you never shrink the number of processors that are active working on the problem. At every stage, you're eliminating some number of elements by recursion, just like the weighted median selection. So those are 2 extremes. And then both of them are successfully employed in practice. Longer answer to a short question. It's okay, nested parallelism is done. It is theoretically one of the easiest subclasses of problems that's been studied. The harder ones is when there are arbitrary dependencies to each other. Other questions? I thought this class would end early, not late, but here we are.